Okay, today we're going to talk about probability distributions and expected value. And then I have a worksheet for you. They don't have a delta math, unfortunately. So probability distributions are functions that assign a probability to each outcome of a sample space for the experiment. We're just going to look at a few examples of these. It's not a huge section of our work, and then we're going to move on. So example 1. Teo and Henry are running for president of student council. You will select a campaign button at random from the box containing 3 Teo buttons and 3 Henry buttons. You will record the number of Teo buttons that you get. What is the theoretical probability distribution for the sample space? 0, 1. Now, there's a few things I want to tell you about this. First of all, theoretical probability is pure odds for what should or can happen, not what does happen. So I'm not pulling and telling you what I got. I'm saying, oh, if it's 3 and 3, then they should have equal probability. Okay, the sample space represents the possible outcomes for this trial. You could select 0 for Teo, because you're pulling one button, so you could get 0, or you could get 1. Okay, so that shows us that 0 or 1. Now, since the outcomes of this are equally likely, the probability of him getting 0 or the probability of him getting 1 are both 1/2. Okay? That's all there is to it. That's the probability distribution. It's probability of 0 is 1/2, probability of 1 is 1/2. Okay, slightly changing the problem. Now you plan to select a button at random, put it back in the box, and then select another button at random. What is the probability distribution for this situation? So now I'm selecting 2 buttons. So this time the sample space is I could get 0 button, 1 button, or 2 Teo buttons, okay? Now, because this is a binomial experiment, because the chances of success and failure are equally likely, we could use the binomial formula to figure out the odds for our probability distribution. So remember, this is what we did last time, that binomial formula. So if I want to know the probability of him getting 0, because remember, a probability distribution just tells us the probability of each outcome in our sample space. So the probability of him getting 0 out of 2 trials. So we have 2C0, plug it all in, we get 0.25. Probability of him getting his button once out of 2 trials, we get 0.5. And the probability of him getting it twice out of 2 trials is 0.25. Okay? So our actual probability distribution then is just the probability of 0 is 1/4, the probability of 1 is 1/2, probability of twice is 1/4. If the probabilities in our distribution are all the same, we call it a uniform distribution. So part A would be uniform because the probability of each is 1/2. Part B would not be uniform because 1/4, 1/2, and 1/4 are not all the same. Okay? All right, that is all we're going to do with probability distribution. Okay, now expected value is where I think this actually gets interesting. You can definitely see the use when we get to some of these problems. And expected value is just the sum of the value of each outcome times the probability of that outcome, which makes no sense until we start looking at examples. We use expected value to predict the value of something when it's not a uniform distribution. The probabilities of different outcomes vary. Okay, so let's look at how we're going to use this. The table shows data on sales in 1 month for each item on a restaurant menu. To estimate future profits, the owner evaluates the average profit from each meal. Okay, so this is his data. He says, okay, if I serve stew, I make 34-cent profit per serving. I sell stew 12% of the time. Soup is 41 cents, 7%, etc. So based on this data, what is the average profit that the owner can expect to make from each meal? I feel like this is actually useful. Okay, so for expected value, each time we take the value of the outcome times the probability of it occurring. So here, the value is he makes 34 cents. And remember, we turn percent into a decimal, so that's 0.12% of the time. Okay, he makes 41 cents, 0.07% of the time. We're adding the individual things, and we end up getting, when I evaluate that, 0.6203. Okay, what that tells us is the owner can expect to earn 62 cents per meal he serves. Kind of interesting, right? So then if he wanted to know the expected profit for the next 200 meals ordered, we could just take that 62 cents, that 0.6203, times the 200 meals, and I would find out he'd make $124.06. I sure hope that owner serves lots and lots of people every day. Okay, another example of this. A charity is considering a fundraising event in which donors will pay $1 to spin the wheel 3 times. We want to know the expected payoff for the charity for each game. So the rules of the game are even threes. You spin 3 times, If you get 3 even numbers, you win $4. If you don't get your 3 even numbers, you just lose the dollar you paid. Each section in the wheel is the same size. So to find expected value, we need the probability of the spinner getting 3 evens or not. Since this is a binomial experiment, because each spin is independent, odds of even spin is the same as the odds of an odd spin. So if I wanted to, I could just use that binomial formula to find my probability. So 3 spins, they need 3 evens. So we do 3C3, okay, the whole thing, and I get that their chances of success, the probability of them winning, okay, against the charity is 1/8, okay? Or depending on how you look at it, that's when the charity is losing, has to pay, because we're trying to look at this from the charity perspective. So the charity wins 7/8 of the time, okay, because the spinner only wins 1/8 of the time. So the charity gets $1 7/8 of the time, okay, and then the charity has to pay $3 1/8 of the time. Now that's -3 because they charge $1, but they have to pay 4, so they're -3 down. Okay, so they're paying $3 1/8 of the time. When I evaluate that expected value, I get 1/2. What that tells me is that the charity can expect to earn 50 cents or a half for every game, every person who walks up. Okay, that's what it's going to average out to be. Now, if we were looking at it from the opposite perspective, what would be the expected payoff for the person playing the game? Now, the person playing the game is losing their $1 7/8 of the time, but they're winning the $3 1/8 of the time. So they can expect to lose 50 cents a game. I mean, I know that's not average, remember, because they're paying $1. So sometimes they're going to lose and sometimes they're going to win. But if they played 10 games, they would come out to like -50 cents a game or -$5 over the course of 10 games. Okay. Kind of interesting, right? All right, last example. Angela has $10 to spend on game tickets for a charity fundraiser. Which game should she play to create a greater expected payoff for the charity? So here's the situation. Game A has a ticket cost of $5. If you win, the prize is $2,000, and this is your chance of winning. Okay, Game B has a ticket cost of $10. If you win, this is how much you win, and there's your chance of winning. Now, when we do expected value, remember we look at not just their chance of winning, but their chance of losing, because when they lose that $5. So if the chance of winning is 0.001 in this first situation, okay, then the chance of losing is 1 minus that, or 0.999. So we're going to look at this from the charity point of view. So the charity's taking in $5 positive dollars 0.999% of the time, okay? And then they're paying out $2,000 0.01% of the time. So I just evaluate that. What I find is that they win, the charity makes about 4.995 a game, and I'm going to multiply that by, or sorry, not point, I messed that up. This is 4.995 and this is -2. So the charity wins, 2.995 on average per game. But because I had $10 to play with, I'm going to pay 2 games. So the charity would win about $6, okay, if I play game A, which is, we're trying to make the charity money. If I play game B, okay, I pay $10 to play, okay, the charity has a 0.999% chance of me losing, them winning. If then I win $50,000, this little, 0.0001% of the time, so the charity comes out with about $5 in that case. But I can only play 1 game with my $10. So if the charity is actually making more money if I spent my money playing game A, because there they make about $6 versus here $5. Okay. If I wanted a better chance of making money, I would go with game B. But because I'm trying to help the charity, I go with game A. All right. Today's worksheet. If you have questions, get on Zoom and ask me.